Great, thanks. So yeah, today we're looking forward to hearing from the emerging leaders in ocean science. And I wanted to start off, I was curious if you all in the virtual audience can think of some of the early career scientists and other professionals that you've interacted with, and kind of thinking about what are some of the unique contributions and assets that these kind of emerging leaders bring to marine science and practice fields. And so I wanted to just share from my perspective, I really believe that we need these diverse perspectives and new ways of thinking to solve a lot of the global challenges that we're facing today and work towards the solutions that we so urgently need. And so I really think that early career scientists, like the ones we'll hear from today, can bring these innovative ideas and novel ways of thinking to this very complex ocean research and practice topics. And so the other piece is that early career scientists can really, they're helping to shape the vision and future of ocean science, and thus are essential leaders in the field. And in this spirit, the Oceanography Society is recognizing the essential role and contribution of early career scientists to the fields of ocean science. And Jenny will talk a bit more about this award, including the selection and nomination process a little bit later. But next, I'll go to introducing our captains today. And so I'll start off with giving a brief introduction. I'm Erin Satterthwaite, and I'm going to be the moderator for today. And I'm a researcher and extension specialist with California Sea Grant and the Cal Coffee program at Scripps Institution of Oceanography in California. And I also serve as the early career counselor on the TOS Council. And I'm really honored to be hosting this event because I've been very passionate about including early career professionals in ocean science and sustainability topics. And so it's really a treat to be part of this event. And so we're really excited to introduce our outstanding award recipients. So the first is James Watson. James, if you want to introduce yourself.
Hi, everyone. Thanks, Erin, and Lindsay and Jenny also for organizing all of this. Yeah, I'm James Watson. I'm an associate professor at Oregon State University. And yeah, I've been studying the oceans for the last 10 or 15 years. And so super excited to be able to talk with all of you about a bit about the research that I've been doing. Great to be here.
Great, thanks, James. And then next we have April Abbott, if you'd like to come on.
Hi, everyone. First, I just want to echo James and thanking everyone in the Oceanographic Society and Seabird for putting this on tonight. I'm a geochemist, so I'm really interested in how the oceans interact with the underlying sediment, and I'm excited to talk to everyone tonight about a little bit of our findings.
Awesome. Thanks, April. And so next, I just wanted to give a quick overview. So to honor these amazing scientists that you'll hear from, we have a great lineup and celebration ahead. So currently we're in the introduction and housekeeping phase. We'll have next the sponsor sessions and then the awardees presentations. That'll be followed by an exciting giveaway. So you'll hear who the winners are from that. The conclusion, and then we'll have a happy hour that will provide some more details later, but it's an in-person happy hour in Seattle. So with that, if you have questions throughout the webinar, do please put them in the chat or the Q&A, because we'd love to kind of interact with you throughout. Great, so the next piece is that we'll have a word from our sponsors. So Jenny from the Oceanography Society and Calvin from Seabird Scientific will be giving some background and overview for this event. So Jenny, if you'd like to come on.
Hello, everyone. Thank you for joining us today. And I just wanted to talk a little bit about the Oceanography Society and the TOS Early Career Award. The Oceanography Society was started in 1988, and one of our missions is to promote communication among different disciplines in oceanography. And we do that through Oceanography Magazine and through convening conferences, and also in highlighting the achievements of members of our community. And the TOS Early Career Award was started in 2021 after the governing council of the society wanted to figure out different ways to reach out to other members of the community. And you can see on the screen that the criteria for the award is listed. We are going to give it every 2 years. And so the first set of awards was provided in 2021. And ideally, we would have loved to have recognized James and April at the 2022 Ocean Sciences meeting in person. But since we met virtually, we thought, well, it'd be great to do a standalone recognition for them. And that's how the idea for this webinar celebration came about. And if I could have the next slide, please. And I just wanted to call your attention to the nomination procedure and eligibility. If you go to tos.org and look under awards, you can read about this award and all the other ones. And we did put a pause on nominations of awards for 1 year while the governing council works to expand the reach of the awards and make sure that no undue barriers have been put in place that would discourage nominations. And so we did move the nomination by 1 year. So the next nomination deadline is October 31st, 2023. And we are allowing nominations for persons who are within 12 years of earning their highest degree. After 2023, that will go back down to within 10 years. But we didn't want to penalize anyone who would have been nominated for this October 31st, 2022 deadline. And I'm happy to answer any questions about the Oceanography Society or the awards. My email is jenny@tos.org, and I'll put that in the chat. And I look forward to hearing from James and April. Thank you very much. And I'm now happy to introduce Calvin Lewin of Seabird Scientific, who is, Seabird is the co-host of this event.
Thanks, Jenny. Hi, everyone. I am Calvin Lewin. I am the Technical Sales Director here at Seabird Scientific. I've been with Seabird for almost 17 years now, and my team and I support many of our key accounts globally, our OEM partners, and some of our international sales channel partners. If you're not familiar with Seabird Scientific, we are headquartered in Bellevue, Washington. That's about 10 miles east of Seattle. We've got a diverse team of over 200 associates worldwide, primarily in the US, Europe, China, and India, that are all passionate about providing best-in-class sensors and systems for oceanographic research and environmental water quality monitoring. We also have a number of scientists on staff in various different roles across the organization. That helps us ground us in one of our goals to power science-based decisions for a better ocean. Our products are used in numerous critical environment research and monitoring efforts. And as part of our commitment to advancing the science of ocean measurement, we're deeply invested in engineering, metrology, calibration, software development, scientific analysis, and other essential technologies that make our instruments more accurate, reliable, and broadly useful. Next slide, please. This is a fun slide that shows a number of logos of some of the customers that we work with around the world. We work with research institutes, ocean observing programs, national and local government agencies, environmental consulting businesses, and the various navies around the world. So on behalf of everyone at Seabird Scientific, I want to say congratulations to both April and James for receiving the Oceanographic Society's Early Career Award and for your research contributions and impact. We will hear first and next from April Abbott. So over to you, April.
Thank you, Calvin. Hello, everyone, and thanks again for coming. Today, I want to talk to you a little bit about my research on the influence of the sediments on trace element cycling in the ocean. So to get started, just a quick orientation, we're going to be looking mainly at the rare earth elements. So way down at the bottom of the periodic table, where especially if you talk to non-chemists, tends to get ignored quite a bit. And I'll be focusing a lot of my talk on neodymium. Neodymium has been used for several decades as a tracer of water mass circulation and as a proxy of water mass circulation changes in the past. It's considered a robust tracer. It's not as prone to biological effects as some of the other options, such as carbon. But unfortunately, neodymium itself does have some issues. The reason neodymium is such a unique tracer for water mass circulation is that our continental sources, so the continents and the land that provides most of the neodymium to the ocean originally, are heterogeneous. And that means that because neodymium is in the ocean for a short amount of time, a time much less than the time that it takes the ocean to completely mix, you end up getting a unique signature of neodymium isotopes based on where water mass forms. And this appears to work really well in the modern ocean. So what you're looking at right now is a transect from the southern edge of the Atlantic on the left-hand side of your screen up through the Atlantic to the northern edge on your right-hand screen. The colors show salinity, so we can see the major water masses indicated as different colors by their unique salinities, with the prominent features being the North Atlantic deep water in yellow and the Antarctic bottom water in green. The reason I'm showing this is to show the kind of promise behind neodymium as a water mass tracer. So we have 6 stations here where neodymium isotopes were taken at multiple depths, shown by the little white boxes. This figure from a 1999 paper highlights that anytime we're in the core of a water mass, such as the North Atlantic deep water, we see an epsilon neodymium value that matches that expected for that water mass. So while the scales for epsilon neodymium are different at each station, that red dashed line going vertically at each station shows negative 13.5, considered the characteristic signature of North Atlantic deep water. And as long as we're in the heart of that water mass, our measured values approach that negative 13.5 and fall on that line. When we start to get water mass mixing, as indicated here by a change in color or change in salinity, we see deviation from the line, but not before. This is thought to be because the neodymium's coming in through rivers, mainly in dissolved, but some particulates as well, and thus being set at the water mass's location of origin, or where we're forming that deep water mass. But work about 15 or 20 years ago showed that the budgets don't quite work. And by not quite work, they're missing quite a bit. So this is a figure from one paper in 2009 that was one in a series of about 5 papers that suggested we only can account for about 5% of the neodymium coming into the ocean. And this presents a problem if we want to use neodymium as a conservative tracer. It's like trying to balance a checkbook with $100 and not knowing where $95 came from. So the question we set out to answer is, what if the primary source of neodymium to the ocean is actually from the sediments instead? What if instead of a top-down source, we actually have a bottom-up driven budget? Why did we turn to a bottom-up driven budget? Well, there was a couple of problems with neodymium that started to raise some flags and ask if maybe the sediments were playing an important role. First of all, neodymium isotopes are considered conservative, and thus why they can be used as a water mass tracer. but we know neodymium concentrations. So the element neodymium itself does not behave conservatively in the ocean. And instead, we see more of a scavenged profile with very low concentrations in surface water and very high concentrations at depth. Well, high in terms of a rare earth element. This was kind of coined the neodymium paradox and left as in kind of accepted that the concentrations were non-conservative, but the isotopes were still considered at least quasi-conservative. The other problem is if we're setting the signature where deep water masses form or where deep water masses subduct, how are we getting a unique signature in the North Pacific in the modern ocean where we don't have deep water formation in the North Pacific? This would suggest non-conservative behavior, at least in the Pacific Basin. And finally, this series of papers that said the budget didn't balance based on riverine input and dust, and that we actually needed 95% more neodymium coming into the ocean to balance the budgets in modern day observations. There were also some literature inconsistencies. So 1985 was the first time that the rare earths, including neodymium, were measured in 4 amps, so one of the sedimentary records used for these reconstructions. And Martin Palmer clearly stated that he believed that they were being derived from the pore waters, from all that water in between the sediment grains. A year later, when they made their first neodymium isotope measurements in 4 amps, they also said that this was coming from pore waters. But because we were unable to measure neodymium isotopes in pore water at the time, somewhere over the next 20 years or so, the assumption was made that pore waters and bottom waters were isotopically identical, and the terms started being used interchangeably in the literature. This isn't a problem if that statement's true, if the pore water isotopes and the bottom water isotopes are the same. It also may not be important if the concentration in the pore water is insignificant compared to the bottom water. The second point we know isn't true. We know the pore water values were higher. But in terms of isotopes, it wasn't until about 5 years ago that we were actually able to take the first neodymium isotope measurements in pore water. And the data I'm about to show you suggests that this assumption, this interchange of pore water and bottom water in terms of terminology, doesn't work for the neodymium isotope system. So the big question was, can we balance the budget of neodymium using a sedimentary source or a benthic flux up out of the sediments? To do this, we had to measure the pore water. The map in the center is showing the location of 4 different research voyages where we were able to collect enough sedimentary pore water to make a neodymium measurement, or at least measure the rare earth concentrations. To put this in perspective, and one of the reasons that we only recently were able to start making these measurements is we need about 5 nanograms of neodymium. While this might be a hard number to comprehend, in terms of the water we need from the pores to get this type of measurement, it's between 500 milliliters and a liter, and we're only getting about 10 milliliters per pore for each interval. What did we find? Well, we found that there was a lot more dissolved neodymium in our pore water than in our overlying water, even when we consider the enrichment of the bottom water compared to surface waters. Assuming a simple diffusive flux, we see that the flux out of the sediments, especially in deeper waters, is on the order of 32 picomoles per centimeter squared per year. Again, this number, unless you've been working with these, is very kind of unintuitive in terms of what that actually means. But a back of the envelope calculation, applying that over the global ocean, shows that that is indeed enough to account for that 95%. Interestingly, and important to note, is that still very tiny amounts of neodymium per centimeter cubed in the sediment. What I mean by this is that the pore water, while greatly enriched by an order of magnitude or 2 compared to bottom water, still has very little neodymium compared to the sediments. So this complicates our ability to measure the sediments to understand pore water. We have to make that measurement on the pore water itself. So this data from the North Pacific demonstrates that the sediments can account for the missing 95% if these North Pacific sites are representative of the global ocean. What I'm showing here now is those same profiles in black. We see the concentrations of the pore water we just saw underneath the overlying water in the white boxes. However, now I've added the isotope values to this. So first, in the blue, I show the pore water isotope values. And while there is some variation, especially at the middle site, I've indicated an average value for purpose of discussion in blue. The gray bars in the white boxes at the top are the sea level values. In the shallow site on the left, you only see one average value for the entire water column. And on the deeper columns, the deeper sites in the middle and on the right of the screen, you can see our distinct bottom water value. What I want you to note is that this value shown in gray are measured or are observed seawater neodymium values is very much shifted from the green lines. And why that's important is these green lines are the neodymium predicted by conservative mixing. So if we didn't have an additional influence, the measured value should be closer to what you see in green. Given that we have pore water neodymium values for these sites, and these were the first ones we were able to measure, we can see that the observed seawater falls in between the predicted and the pore water values. The seawater is the closest to the pore water values at the site where we have the biggest flux. This means that where these authigenic phases, where the sediment record that we use for ocean circulation reconstructions is inherited, whether that's at the bottom, in the bottom water, or whether that's in the sediment column itself, is very important because pore water and bottom water are not interchangeable in terms of their isotope values. So in order to understand the importance of this and see whether our flux calculations make sense in terms of a budget model, we had to understand how widespread this process was. To do that, we went to the Tasman Sea and took 3 more core sites, which showed a similar flux out of the sediment. Halfway unexpected because these are calcareous sediments, which were thought to have less of an influence on the rare earth cycles. But what I wanted to highlight from this particular cruise was actually the 2 sets of water samples. Both sampled into the circumpolar deep water, but we were only about 10 degrees apart in terms of latitude at the 2 stations. We confirmed with temperature salinity that we were sampling the same bottom water masses. And I can indicate on this graph kind of 500 meters to convince you that the only place we had deviations in water masses were at the surface. Despite the close proximity and the calcareous sediments at the bottom, the seawater in the Tasman tells a very similar story to what our sedimentary pore waters have, with a near doubling of concentrations in neodymium along the circumpolar deep water flow path from CTD 23, as it's labeled on the map, to the northern site at CTD 54. Our concentration is doubling in less than 10 degrees latitude. This is a huge change that supports non-conservative behavior of neodymium in terms of concentrations, even over calcareous sediments. And we suspect, although we don't have the data yet, that it means a change for the isotopes as well. But in order to be able to apply this and answer bigger questions in terms of where the benthic flux is important in the modern, but also the paleo, we need a more mechanistic understanding, going out and collecting 500 milliliters to a liter of pore water from sites, numerous sites, in order to be able to cover every possible basis is unrealistic. So we need to understand mechanistically what's driving the flux. And this is where being able to compare the North Pacific with the South Pacific became particularly interesting. In the North Pacific, we have a lot of more terrestrial derived sediments consisting of quartz, as you see here in pink, feldspars, some clay minerals like chlorite and illite. When we move into the Tasman, it's a very different sediment type. It's dominated by carbonates, largely biogenic carbonates. You can see some kind of crushed forams in the image on the left, and quartz. And despite these very different sediment compositions, we saw a similar magnitude indicated by the pore water profiles. So this raises the question, what's actually controlling the magnitude of the sedimentary source? Since then, I've done a lot of work to look at the role of authigenic clays, largely because the rare earths have traditionally been associated with iron. And when we put these sediments underneath an SEM or a scanning electron microscope, we said that the iron is not associated with the unique oxide or oxyhydroxide phases, but is rather associated with the clay minerals, particularly the authigenic clays, such as the smectite on the top of the screen and the glauconite on the bottom of the screen. You see here from the North Pacific. The work with rare earth patterns in these regions is consistent that the difference between what's coming in from the rivers, work done by Bain et al., and what's going out in the glauconites would leave behind essentially the patterns we see in seawater. Additionally, this formation of authigenic clays can drive additional silica weathering in the sediment column and push for new neodymium that would be unique isotopically. And it's this unique isotopically that would allow us to start to explain the neodymium paradox. Some interesting modeling work that John Waydu and colleagues got out earlier this year, essentially saying that this concentration process, this release of neodymium, is always happening, but it's only when we're driving that release of isotopically unique that it's been picked up in the isotope records. So to summarize, this work has shown that sediments are the dominant source of rare earths to the ocean. So we flipped the budget from a top-down model to a bottom-up model. And the fact that the pore water is isotopically unique has implications for paleoproxy interpretations and applications. We're still investigating the role of clay minerals in driving both the benthic flux, but also the observations associated with the paradox. And this role of the sediments in the budget results in widespread overprinting of authigenic records. Combined, this has implications for other trace metals as well. There's been recent publications coming out of the nickel and chromium communities suggesting a benthic flux from the sediment for these trace elements. The figure on your screen right now is showing how the interaction of some of the weathering processes may combine for a unique benthic flux. And to simplify this a little bit, we can look at it in three scenarios to kind of finish off today. One in which our authigenic phases, indicated here by a little cartoon foram, are recording bottom water. This is the more traditional scenario where the proxy is easy to interpret. In our second scenario, the sediments are influencing the bottom water, but our authigenic phase is still recording faithfully the bottom water. It's just now an altered bottom water. And the final scenario allows us to completely decouple the bottom water, and our authigenic phase is being kind of determined within the sediment column itself. So now it's only a function of that pore water value. And as I said, as more work is emerging, particularly from the nickel and chromium, we expect that this framework will be more widely applicable to trace metals, particularly with the work being done by the GeoTraces program to look at trace elements and their isotopes, focusing along the 4 ocean boundaries, including the ocean sediments. So with that, I have a very long list of thank yous for various mentors, colleagues, and students that have made this work possible, as well as, of course, the captains and crews of the ships that it takes to collect these samples. So thank you all, and I'm happy to answer any questions.
Great. Thanks so much, April. I guess I just wanted to encourage, if anyone has questions, please put them in the chat. I think while we're waiting for those, April, I had a question. Well, I actually had two, but I'll start with one. Thank you. This was really interesting. And I just want to say I loved your metaphor about the balancing the checkbook. That really resonated with me. It's a super neat way to think about it. And just at the end, you mentioned that this work, kind of has these broader applications. And I was curious what next steps you're most excited for in your research, or kind of where you're moving. And
so there's a couple. One of the ones I'm most excited for is we keep getting this general response. So when we first went to the Pacific and we said, look, there's a problem. We have a lot of neodymium in the pore waters. It's not the same isotopically as the bottom water. Their general response you got was, well, of course it's a problem. You went to the North Pacific. You're going to see a problem in the North Pacific. Like, check out calcareous sediments. They're not going to have the same problem. And then went to the Tasman Sea, said, well, look, calcareous sediments are kind of behaving the same. And it's still the Pacific. Of course, it's still a problem. So we have a project scheduled to go to the North Atlantic. So kind of the heart of where the proxy's been, I guess, developed, and see what we can find there, whether we have the same amount of influence of the sediments in the North Atlantic, and if so, what that means for kind of reconstructing Atlantic overturning over the last however many years. Because at least looking at glacial interglacial records in the North Atlantic, the authigenic and the detrital records are almost completely correlated. They're too well correlated for me to believe they're independent. So I'm really excited to see kind of what we find in the North Atlantic.
Awesome. Thanks. That's great. I guess I'm curious, have you seen any questions come through?
I just lost my Q&A. I don't see any.
Okay, great. Well, I'll take another one as we wait, if that's all right. Yeah, so I think the other one I was just curious was if there's some kind of memorable or favorite part of this work. Just looking at this thank you slide, it looks like, it's taken a lot of effort, a lot of people, a lot of teams to carry this out. And so, yeah, just curious, memorable, favorite, fun story, something great. Yeah,
they're all memorable for different reasons. I do remember being on one cruise where we're using a multi-core. We're taking hopefully 6 to 8 cores at a time, because it usually takes us 30 cores to get enough water to make these multiple measurements down core. And multi-core tubes are only maybe a ½ meter long and something like that. And somehow we managed to get a sea urchin right in the center of the core tube. Didn't injure it, didn't anything, just filled up the entire core tube, perfectly aligned in the center of the core, which was unfortunate given that was our upper 6 centimeters. So we couldn't do any measurements on that particular core, but it was really incredible to see. Another voyage, we had the multi-core going over at night, and the lights were just enough to bring up the squid. So we had a school of 30 dolphins playing in the ship's light while we waited the 4 hours for the core to come back on board. So it's just always spectacular.
That sounds amazing. That must have been so neat to see. Great. Well, thank you so much, April. This was, super fascinating and such a body of work that you've put together. So
thank you again, and thank you for hosting. And I think next up is our other awards recipient, James. So let me stop sharing so you can have the screen.
Thank you. And April, yeah, that was a super cool talk. It was great learning about that. It's been a while since I've done any chemical oceanography, so that was an education for me. Can I confirm, Erin, can you see my slides?
Now we can. Yep. Looks great.
Okay, and yep, and thanks everyone who's come here and to listen to these talks, and again, thanks the Oceanography Society for setting this all up. It's really great to do so. So, title of my talk is going to be the complexity of our oceans, and I just wanted to start here All right, so I don't know if you've read all 3,500 pages of the latest IPCC, so the Intergovernmental Panel on Climate Change Assessment Report. But the take-home message is that climate change is getting real, right? If it hasn't already, for many millions of people around the world. So this means that there's an urgency to our science. Now, more than ever, we need to better understand our oceans so that we can develop realistic climate adaptation strategies and indeed carbon dioxide removal technologies that actually work. But none of this is easy because we live in a complex, dynamic world where the subcomponents of the Earth system are highly connected and exhibit non-linear dynamics that are hard to predict, least control. Now, this is true at sea just as much as it is on land, even though you might look at the oceans and imagine a rather simple system, we know that it is quite the opposite. So in this talk, I just wanted to go through several aspects of my work that touch upon the different types of complexity exhibited by the oceans. Specifically, we'll talk about how ocean currents move planktonic organisms around, creating complex spatial patterns of connectivity between marine habitats. Then we'll briefly explore the connectivity of marine food webs and how allometric scaling laws can help us model future changes in the abundance of fish. And then we'll talk about the complexity inherent to our use of the seas, primarily through fishing. And I'll finish by describing new methods that are being developed to manage this form of complexity. And I'll give a nod to these two guys, Elinor Ostrom and Ken Arrow, both Nobel award-winning economists. So first up, though, spatial complexity. So this is work that was spearheaded by Dave Siegel at UC Santa Barbara and Satoshi Mitarai at OIST, the Okinawa Institute for Science and Technology. He's there now, but this was about 10 years ago, but the results are still relevant today. So here we were trying to explore how ocean currents can disperse fish larvae from one place to another, creating complex spatial networks of sources and sinks. My contribution here was to explore the usefulness of network theory for helping to identify important habitats. The idea being that just like in a social network, there are those nodes that are highly connected. So like my wife, and those that are not highly connected, like me. So if my wife left a party, you would notice. But if I left, there would actually be no appreciable change whatsoever. So just like in the social network example, you have the same situation in terms of nearshore habitat connectivity. Some places, so rocky reefs, in the case of the Southern California Bight where we did this work, they're more connected than others, and this is important to the design of marine protected areas. And that was the motivation for the work back when California was putting in place a whole system of marine protected areas. But the application of network theory to marine connectivity extends beyond MPAs, marine protected areas. So for example, in terms of predicting the impacts of regional disasters like an oil spill. And indeed, this work is also helping us to better understand why we observe patterns of planktonic biodiversity, specifically through comparing estimates of global connectivity with measures of biodiversity gained from ambitious global circumnavigation studies like the recent Malaspina expedition. We've been testing hypotheses for the role of ocean currents in structuring marine planktonic communities at a global scale. Now, in addition to the spatial complexity that I've just discussed, another very important form of complexity in our oceans is in terms of ecological complexity. So marine food webs can be complex, all the way from viruses to bacteria, to phytoplankton, to zooplankton, and then all the way up to larger and larger organisms. This complex web of interactions can be overwhelming. And indeed, theoretical ecologists have sought abstractions that are more amenable to modeling, but that still remain useful. Now, one way of looking at marine food webs is through their size spectra. And what I mean by this is that if you observe things feeding in the oceans, you can find a recurring pattern. So specifically, larger things tend to eat smaller things. as seen in this fossil that I found while walking around Princeton University once. It's a fossil of a medium-sized fish choking, and I presume dying, while trying to eat a smaller sized fish. You can go further into this, and if you look at the biomass of marine organisms as a function of their typical body mass, then you can find what are called these allometric scaling laws. Essentially, there are consistent patterns seen around the world where there are slightly less large body organisms than small bodied organisms. You can use these general patterns to construct models of marine food webs that circumvent the need for modeling everything and instead boil things down to the size-based feeding relationships. And in doing so, we can then model marine food webs from the smallest organisms up to the largest at a global scale. So this was work that I helped out with Jorge Sarmiento, Charlie Stock, and now Colleen Petrick, who's at Scripps, is really pushing the envelope on what can be done with this kind of global scale, size-based fish modeling. The final form of complexity that I wanted to discuss is the complexity of human interactions with our oceans. So in the previous figure, you might have noticed that something was missing. Specifically, there was no mention of human impacts on the structure and dynamics of marine food webs. And omitting human activities would be erroneous. New data streams on the location of fishing vessels are showing that humans fish everywhere, in every ocean, and that this has greatly altered the structure of marine food webs around the world. Now, we fish for two reasons. First, some people fish for food, but by and large, most people fish for income. And so it's an important economic question to ask, which is how valuable are the oceans? Now, this is a question that has been posed for decades, and not just at the sea. The Nobel Award-winning economist Ken Arrow did foundational work on ideas of inclusive wealth, which led to theories of natural capital, which led to ideas of ecosystem services, which is maybe the term that is more popular today. And it's quite a simple thing to ask. What is the monetary value of Mount Bachelor, where I want to go skiing this winter, or Detroit Lake, where I sometimes go in the summer? The same question can be posed of the oceans. How valuable is the Northeastern Pacific to us, to me here in the Pacific Northwest of North America? And so, working with John Woodall, we've been using and advancing new economic theory for making this calculation. And in doing so, we're hoping to inform issues such as the closure of the crab fisheries this year. We're hoping to answer the question of whether this kind of event is related to climate change, and if so, can we attribute these losses to a specific climate shock? Now, this is important because it relates to how we manage these kinds of climate shocks, these kinds of risks. And here, I'm actually talking about insurance. On the right, you can see two kinds of droughts, one on land and one at sea. The issue is that on land, farmers can buy insurance to protect themselves from the impacts of a climate shock like a drought. But fishermen cannot buy insurance in a similar way, even though the causes and impacts are analogous. So I've been working with Phil Levin at UW and some friends in Australia to figure out why insurance for marine climate shocks is not available, and what it would take to make them available so that the economic impacts of closures, like in fisheries closures, like we're experiencing with crab this year, are lessened. Now, these shocks to our marine systems are going to alter where fishermen go. Essentially, with climate change, where fish is caught is going to change. And I want you to think about the Arctic, which is currently off limits to fishing, but in a few decades, who knows? And let's put this in the context of the Chinese distant water fishing fleet, which comprises approximately 17,000 fishing vessels. Now, this fleet has conducted some contentious acts in recent times. For example, here on the right is a map of 300 Chinese fishing vessels that were operating just outside the Galapagos exclusive economic zone, prompting action by the Ecuadorian and Peruvian coast guards. Now, climate change impacts on where fish are and then where fishing happens is going to intensify these kinds of fisheries disputes and even open conflicts. And so my students, Nico and Sierra, have studied how fisheries conflicts emerge with a particular focus on Puerto Rico. And indeed, illegal fishing is thought to be a main driver. So we've also been working on developing new machine learning methods for predicting illegal fishing. Essentially, by combining satellite-derived estimates of oceanographic conditions for certain regions, it is possible to predict where fishing is going to happen and by who. For places like the Patagonia Shelf, which has experienced chronic levels of illegal fishing, we've shown that machine learning can predict with a good level of accuracy when distant water fleets will incur into the Argentine EEZ, Exclusive Economic Zone. And this kind of information is really valuable for Coast Guards tasked with dealing with illegal fishing. But Coast Guards won't be able to solve this problem at large. What we've learned is that it will only be through a massive effort of cooperation that nations can avoid coming into conflict with one another over shifting access to marine resources. So who should cooperate with who? Using climate change projections from the Community Model Intercomparison Project, Stephen Johnson and I examined where contemporary local ocean conditions will move at certain points in the future. So put it in another way, the ocean conditions here off Oregon, where I live, or even off Washington, for that matter, those conditions will actually be up by British Columbia or even Alaska at some point in the future. This information is helping us to identify who should cooperate with who, or as we're calling them, climate cooperatives. Now, this is just like the concept of sister cities. For example, I live in Corvallis, Oregon, which has two sister cities, Uzhhorod in the Ukraine and Gondar in Ethiopia. And what we're proposing is that climate cooperatives are those communities connected through space and time by shifting environmental conditions that have collective knowledge to help adapt to climate change. And so this is actually why I'm showing you a picture of Ellen Ostrom, the Nobel Award-winning economist, whose decades of research on cooperation showed us how institutions need to be designed to help overcome asymmetry in access to natural resources. And that's the last thought from this talk. In my lab, we like to say that cooperation is humanity's superpower. And together with the technological innovations that we're pushing forward, especially in the context of carbon dioxide removal, we can turn the great challenges facing us in the coming decades into opportunities for a bright future. Thank you so much. And that's the end of my talk. Happy to take some questions.
Thanks so much, James. That's amazing. That's awesome. Thanks for a really cool talk. Let me just see. I don't see any questions, but as folks are thinking of questions, there's a lot of compelling components that at least I wanted to touch on. I think I just wanted to say I really appreciated your quote, and I hope I got it right, but cooperation is humanity's superpower. I think that's a really neat way of thinking about it. And I feel like, yeah, just the way you articulated that really stands out to me. Yeah, I think for me, one of the questions I had was maybe looking forward, how you see some of this kind of the pieces of cooperation, network analysis, and kind of the social ecological systems components, how you see some of that, like where you see us moving in the future to actually like address some of, like you mentioned, you started off with the IPCC report. How do you see kind of integrating those across scales and I guess, disciplines, other things like that?
Yeah, sure. So I think there's a few things to think about there, which is when you want to solve a problem, specifically like what the economists might call a collective action problem. It's a problem that can only be solved by working together. This is climate change, and there are other collective action problems too. You first have to understand who the actors are, who's got skin in the game, who's going to lose out, who's going to win, and bring them together, of course. and you have to quantify actually the problem for those actors. Like I just said, like who is going to win, who is going to lose. There are going to be lots of losers in terms of climate change, but strangely there might be some relative winners. And it's only by being honest about that and acknowledging it, then the conversation can start. But then going beyond that, you know, there's just the hard work of developing cooperative and collaborative solutions. And I'm no expert in that, but what I've seen is that there is there's everything. There's so many disciplines dedicated to that. Everything from economics and game theory to dispute solutioneers, for a better word, who bring people together to solve problems. But I think what we're seeing is that effective coordination has to come from the ground up. Actually, people need to form bonds between each other, collaborations between each other at the grassroots. So these maybe sub-national level, regions, states, cities, they need to start the process at that level and then grow larger and larger groups, and the momentum builds from there. Yes, of course, structuring solutions from the top down is also a solution space that should be explored, but there's a lot of power to be had from grassroots initiatives to make change happen. But again, that's I mean, there are other people who could speak more eloquently to how we can solve collective action problems.
Great, thanks, James. That's great. And actually, kind of along those lines, there's a question in the chat from John Ewald, kind of going along this, when you mentioned the different scales. The question is, how do you see us, the United States, working on this concept, and then also at the United Nations levels?
Yeah, okay. Again, there's going to be other people in a far better place to answer that question, but maybe just personally, I mean, we have these institutions that are places where we can come together and discuss and try and solve the problems, and ignoring them is not a step forward, it would be a step back. So embracing the institutions like the United Nations, being part of the conversations, COP27 is going on right now. Yes, there's, we can discuss the utility, the effectiveness of any of these things, for sure. There's a lot left to be desired, right? But stepping away from them is not going to improve things. What I would like to see, though, and I think in at least what I've seen in the last 5 years or so, maybe a bit longer, is a groundswell change in the population at large. Actually, I just have a sense that the majority of people are waking up to this reality, right? The conversation's no more. I mean, my conversations with my in-laws is no longer about whether climate change is real or not. It's about what we're going to do about it. And so maybe that's true of other in-laws as well. But we're seeing this it's certainly in terms of the youth today, the youth participation in the conversation about how we need to get our stuff together and solve this problem, which we can do and we will do, hopefully. We must do, right? And so, yeah, you have these formal institutions like the UN, but I'm really seeing new formal institutions, but also informal institutions growing. And when I say institutions, I also mean movements, like the Sunrise Movement, say, that is extremely powerful for getting things done.
Fabulous. Thanks for that. And we had one. Oh yeah, no, go ahead.
Yeah, sorry, I was going on. Yeah, so Gregory, I can send you, I mean, if you just Google James Watson, Stephen Johnson, Ocean Novelty, that was the paper we just published in One Earth on it. And we're going to be submitting another paper on climate cooperatives very shortly.
Great. Well, thank you so much, James. I really appreciate this. And yeah, I guess if I think we have time for one more question. I wanted to see if you wanted to share any of the biggest challenges in your work or in going out to sea.
Yeah, so fine. Okay, so what you might have seen or guessed from seeing in my talk is I don't go out to sea because I have these grand ambitions when I was younger, grand ambitions for going out to sea and being an ocean-going oceanographer, but it became quickly apparent that that wasn't meant to be, because I get horrendously seasick. And even though every 5 years I seem to forget and try to go out, I just like spend hours puking in front of my students. It's not good. It's not good at all. But it's sent me down a route that I'm very appreciative of. All the stuff you've seen came from sort of embracing the data sets that are already out there, the modeling, the computer simulation techniques that I've picked up along the way. And so, yeah, you can still do a lot as an oceanographer that doesn't like to get wet.
Awesome. Thanks for that. That's such an interesting story. I know it's always funny how paths change over time. Great. Well, thanks again, James. That was fabulous. And I think so. Next, we'll transition from these amazing presentations. And I just want to give a virtual round of applause again to April and James for sharing your work and for such compelling presentations. And so we're going to transition to the giveaway. And so as many of you on the call may have seen, you were eligible to win for this giveaway if you registered and then attended the webinar. So thanks again for being here. And the prizes for this actually include a box of Seabird Scientific supplies, a 2020 Apple iPad with a compostable pellet case, and then a $250 gift card to a charity of your choice, which you will be sent via email. And so that's the prize. And drum roll, the winner is Isuri Capuch. And Isuri, if you're here, you'll receive an email from Lindsay from Seabird Scientific with directions on how to claim your prize. So congratulations and thanks again for being here. And so with that, the next part of our programming is actually following this event. There will be an in-person happy hour if you're in Seattle, and it will be from 5:45 to 7:30 p.m. Pacific time. And really, please join us. This will be a happy hour featuring drinks and appetizers following this ceremony to network with experts in the oceanography community. And it'll be at Skull Beer Hall, which is in Seattle, Washington. And so there is an RSVP required, but you may see in the chat that Lindsay is putting the link to register there. And we really hope to see you tonight. And so with that, we conclude our ceremony, but we really wanted to send it around one more time to see if anyone here on the call has any final words, closing remarks, advice, anything else they'd like to share with the audience before we conclude.
Hi, everyone. This is Jenny Ramarui from the Oceanography Society. And I just want to thank April and James for those great presentations. And I noticed that one extra question that came in that said, 2 excellent presentations today from April and James, stimulating and interesting. How do we support their continued efforts? And I can say from the Oceanography Society, we'll continue to highlight James and April as our award recipients and just spread the word about this event and these great presentations so that others can log in and view their talks. But I really want to thank them and thank Seabird Scientific and Aaron Satterthwaite as our very able host for this great event.
Yeah, this is Calvin from Seabird Scientific. Again, great presentations, April and James, pretty fascinating. And it's really great to kind of see early career scientists like yourself doing this kind of work and really look forward to all the great work you're going to do in the future. So again, congratulations and thank you.
I'll just say thanks again, guys. It's been a pleasure to be here and to interact with the Oceanography Society and Seabird Scientific. Thanks, everyone.
Yeah, I'd just like to echo that. Thank you everyone for arranging this, the Oceanographic Society, Seabird. It's been amazing. And thanks, James, for a really cool talk.
Great. Thanks all. And so we'd really like to thank Jenny and the team at the Oceanography Society for facilitating this award and really making this way to recognize and elevate early career researchers. And then, of course, as others have mentioned, to April and James, a huge congratulations. Yay. And we're grateful for your participation today and for sharing your research. And then we're also extremely grateful to Lindsay and Calvin and the team at Seabird Scientific for facilitating this event and for hosting the happy hour later. And then to all of you for being here to honor and celebrate these fantastic award recipients. So with that, wherever you're located, we hope you have a great rest of your day or evening, and thank you again.